Alright, this is video 3 for Calc 3. We have two book problems that we're going to go over in this video. The first one comes from 4.3, and at 157 it says the equation for heat flow in the xy plane is given by this partial differential equation, that the partial of f with respect to t is equal to the second partial of f with respect to x plus the second partial of f with respect to y. And we're asked to show that the function given here, f of x yt equal e to the minus 2t sine x sine y, is a solution to this differential equation. So what we should do is compute these partials of this function and then just plug them into the equation and see if the relationship holds. So let's compute the partial with respect to t and these second order partials here. We'll compute these. The first guy, let's just write him down. Partial of f with respect to t is equal to, so in this equation here I'm going to treat the sine and the sine x and the sine y as constants because I'm differentiating with respect to t, and I will get a minus 2 e to the minus 2t, and then these constants with respect to t come along for the right there. So that's my partial with respect to t. Now I should calculate second partials with respect to x and y. First I will do the partial with respect to x, and notice I can just write this as the derivative or the partial of the partial, right, of the first partial. And then I can calculate that first partial derivative with respect to x. In that case, I will treat the exponential here as a constant because it is with respect to x, and same with the sine. And I'll only differentiate the sine x here. So I will end up with e to the minus 2t cosine of x, right, because sine goes to cosine when I differentiate sine of y. Now I need to differentiate this the second time with respect to x. So I will not writing my differential operator outside anymore. I will have e to the minus 2t cosine goes to a minus sine x sine of y. Okay, so there's my second partial of f with respect to x. Let's calculate the second partial with respect to y. Same as before, right? I can first calculate the first derivative or the first partial with respect to y and save myself a little effort here. Let's just do this quickly. E to the minus 2t, it will now be sine of x cosine of y, kind of symmetric to the one before, right? And now it is, partial has been calculated, so I won't, not need that. And this, now I take the derivative of this guy with respect to y, and that is going to be e to the minus 2t sine of x. Cosine goes to a minus sign, so that will be sine of y with a negative out front. Okay? Now I need to go back to this equation, this relationship that they told me, this heat equation, and verify that these partials, that the equation holds basically. So let me write down the left-hand side of the equation. It was this. Second partial with respect to y. This guy, if I plug now in what I got here and here, I get what? Minus e to the minus 2t sine x sine y minus e to the minus 2t sine x sine y. Well, what's this equal to? Minus 2 e to the minus 2t sine x sine y. And notice this is exactly this guy right here, my partial with respect to of f with respect to t, excuse me. So, and this is exactly partial of f with respect to t. That's exactly what we wanted. So we can say that the equation is satisfied and the function is a solution to it. Okay, so we would say therefore f is a solution. Okay. Pretty straightforward there, how to do those problems. You just take those derivatives that show up in the equation and then you plug them into the equation to verify that it holds, right? Make sure that both sides of the equation are equal. All right, now let's look at our second question here. It's a little bit longer. It says that electrical resistance R produced by wiring resistors R1 and R2 in parallel can be calculated from the formula 1 over R equals 1 over R1 plus 1 over R2. Okay, if R1 and R2 are measured to be 4 and 6 respectively, and if these measurements are accurate to 0.05 ohms, estimate the maximum possible error in computing R. Okay. So the first thing, let's recall something from class to begin this, or maybe I will set up. Let me just go through this. Maybe you're not a physicist, and the wording of this problem may seem a little bit confusing at first. Let's just reword the problem, okay? Or think about what this means to us in our Calculus 3 class. So our question can be rephrased. Is really something like this. How much does R of R1, R2 change, this function, right, as the point right here moves from moves from R1, R2 equal 4 and 6, right? Those are my ohms that they told me that I was interested in looking at. A distance of 0.05 in the direction of maximum increase. Okay, let me just read through that one more time so you're with me on that. So our question, really, we're trying to decide what is the error in R, given that I have these two measurements for R1 and R2, and this is how accurate they are, right, to plus or minus 0.05. That's the maximum error. And then we're trying to compute from that, given this relationship here, what is the maximum error going to be in computing R? Okay, and so I reworded the question to be something I think a little bit more close to problems that you've seen. How much does the function R here change as the point moves from this guy, right? As I move a point from here, a distance point at 0.05 in the direction of maximum increase, right? Okay, so that's what we're doing here. It's more like a linear or a Calc 3 problem now you see with surfaces, and it kind of gives you an intuition for how this is going to work. Let's break down the problem though. So let's talk about this max increase. So you remember that the directional derivative is at a maximum, or it increases the fastest, this directional derivative, in the direction of the gradient. So let's go ahead and calculate the gradient at the point 4,6. And we know that will be where it increases the max, because we're trying to find maximum possible error. Okay, so first, recall that direction of max increase is in direction of the gradient, like I said. And so let's calculate the gradient. Well, to do that, let me first write, we had this equation, right? 1 over R equal 1 over R1 plus 1 over R2. I can rewrite that as R is equal to 1 over R1 plus 1 over R2, the reciprocal of that, right? Okay, now what I can do, and I'm confident that this number is going to be non-zero, right? I'm not allowed to put in zero values for R and 2, and then this number in here will never give me zero, so I'm not having any trouble taking that reciprocal. Okay, now I can calculate the gradient of R, and that's just going to be these partials. with respect to R1 and R2. And I think that you're comfortable doing this. I will just quickly write down what it would be. You get this from actually, what is that called? A power rule, right? And then a chain rule. That will be squared times, let's see, yeah, 1 over R1 squared. All right, there's a negative here and a negative here, but I think it will just cancel. All right, so I can put that all over the one fraction. How about that? And then 1 over R1 plus 1 over R2 quantity squared times R2 squared. And I want to evaluate this at the point 4, 6. And when you do that, you get, let's see, we got 9 over 25, 4 over 25. And I'm confident that you guys can plug in the R1, a 4 for R1 and a 6 for R2 and shove that into a calculator or do it by hand or whatever you prefer there. So now remember, I'm talking here about the direction of the gradient, and what I've calculated here is the gradient. So if I want direction, I need a unit vector. So direction, remember, implies we need a unit vector. This is not of unit length though, right? So let's find the length of this vector and then divide by this vector by its length so that we get a unit vector. So u, or our unit vector in that direction, will be equal to 9 over 25, 4 over 25, divided by the norm or the length of the vector. And that is going to be equal to about, I'm just going to write it in decimals here, approximately 0.914, 0.406. Okay? Perfect. So this is our unit vector in the direction of the gradient. Okay, so now let's go and talk about what, so we have the direction that it's moving in, right? And now we are interested in, let's go back to our question, the change in R, right, as a function of R1 and R2. And the way that we can find that, you probably saw this in class, is something called the linear approximation formula. So let me just write that. This is a linear approximation formula, and it goes like this, that the change in R is approximately equal to the derivative of R with respect, or the partial of R with respect to R1, plug in the values 4 and 6, times our delta R1 plus the partial of R with respect to R2, evaluated at 0.46, times the partial, or the delta, or the change in R2. Okay. So that's what we have, and then we, so let's just write down what we know in this equation so far. R1 at 4.6, the partial of R with respect to R1 at 4.6, we already know this from the gradient, right? That's going to be 9 over 25. Same with R2, right? The partial with respect to R2, valued at 4 and 6, is going to be 4 over 25. Now I had better figure out what these guys are. Okay, the way to do that is going to be looking at the direction of the gradient, right? Well, the direction of the gradient, they told me, was this little unit vector here. That's what we found out. And now we want to move along this unit vector, right? So if this is my gradient, right, I have this gradient here. Then I made it a unit vector, something. Now I'm told that I move how far along it? Well, it's a distance of 0.05 that I'm going to move along in that direction of maximum increase, right? That's the distance I want to move along it, so I will not go at 1 unit length, I will go 0.05 of that unit distance. And so I will say here that my delta R1, delta R2 is equal to 0.05 times this unit vector that I calculated up here, right? So we will put a 0.914 and 0.406, right? And then from that equation, you know, we get this out, and it's roughly something like 0.045, 0.02. Okay, so that's how that is calculated. And now we can plug in our R1 and our R2, which we calculated here. That's delta R1, delta R2, into the linear approximation formula. So I have delta R1, delta R2 from below, right? 0.045, 0.02. Okay, so I have here that delta R is approximately equal to 9/25 times my delta R1, 0.045, plus 4/25 times 0.02, and this comes out to 0.02 ohms. Right, so that is the approximate change. That's an approximation for the maximum error or the maximum change in delta R. And so that's kind of, I mean, sure, this is a straightforward way of doing the problem, but I hope to give you some kind of geometric interpretation of this. And so I have this little maple worksheet that Andreas has prepared from class. It's on Canvas, and it gives you an idea of how this works. So assume that this little cone right here is the surface 1 over R plus 1 over R1, or it's some surface that I'm trying to approximate, right? Like the one that we were doing for 1 over R plus 1, 1 plus 1 over R plus R2, right? So, and we're maybe looking at this point here, which in our case would be 4, 6. What we did by using that linear approximation formula is we said, instead of looking at this more complicated shape, let me look at a plane which touches it like this. And from the plane, I will make an approximation to the behavior of the function, right? I will approximate the behavior of the function by using this plane. And around this point, it is actually going to be quite accurate. So when we use this linear approximation formula, that is exactly what we're doing. We're saying, let me take a plane which touches the surface or the curve in some way that locally it behaves exactly the same way. And then from that I can tell you something, an approximation about the change in the function or the behavior of the function around that point. Okay, so that's the kind of geometric intuition of this linear approximation formula, looking at a tangent plane. All right, well, I hope this helps you with your homework this week, and that is the end of our video.